All right, beginning lesson number 2, Math 5130. Let's define where we are. From 30,000 feet, so to speak, where are we? Well, in lesson 1, we focused our attention on statistical techniques to statistically describe our sample data. Now we're transitioning from using or statistically describing our sample data to using our sample data to make a generalization about the population from which our data was collected. So the first thing we would do is we need to frame our research question. And I have two different questions here. Both of them deal with measuring glucose levels. One of them, the first one, focuses more on reframing the problem to address the percentage or proportion of those living in a small Appalachian town who are diabetic, and the other actually looks at the mean glucose level. So the two questions are pretty similar in nature, but the way they're posed requires two completely different statistical techniques to address those. So in this video, I'm going to focus on how we would answer the question, what percentage proportion of those living in a small Appalachian town is diabetic? So first thing we would do, again, go out and collect a random sample. We'd measure the glucose level and label each as high or low. Probably not high or low, but probably more high or not high. And I don't know what the standard would be for that. It seems like to me it jumps all over the place. Some people say 100. Some people seem to say 110. I've seen other places that say 120. So I don't know. I analyze data. I don't determine high glucose versus not high glucose. Next thing we would do is statistically describe the sample with frequencies and percentages. Again, circling back to lesson number 1. And then we would write a sentence similar to in a random sample of 200 residents. We saw that 27 were observed to be diabetic and 173 observed as non-diabetic. So we'd write up a statement like that. And again, this is fictional data. I'm just made up the 200, and I didn't really go out and do this. And 27 were diabetic, and I just made that up. So it's just an example to motivate the idea. So the idea here is we want to be able to estimate with confidence. And we do that by constructing something called a confidence interval for proportions. Percentages and proportions are interchangeable. So I tell you, I've already gone ahead and calculated the 95% confidence interval. It's 8.8% to 18.2%. So throughout the rest of the video, we're going to talk about how this calculation was made. I'm going to show you how to make it in StatCrunch. I'm going to tell you the right way and the wrong way to interpret this confidence interval. But again, what you must tattoo to the brain right now is we are using our sample data, this 13.5%, this 27 out of 200 who were observed to be diabetic, to make a statement about rates of diabetes for all residents in this town. So about halfway down, you'll see that I've given you the general form for a confidence interval. Now, we're going to run into confidence intervals like crazy the rest of this term. So it's a pretty good idea to have a decent fundamental understanding of confidence intervals. We're not going to dive into the weeds and look at sampling distributions and normal distributions and construction of t-critical values and all that stuff as I would in an undergrad statistics class. My focus in this class is to teach you to be a researcher in your field. So all that other stuff, if you feel that you need to a review on that, then reach out to Google or Khan Academy or something like that. But in general, confidence interval is your point estimate. That's what we get from our sample. plus or minus something we call a critical value times the standard error. For this problem, our point estimate is 0.135, 27 divided by 200. Our critical value, a little bit more about that later, is 1.96, and our standard error is 0.0242. Again, I've already calculated the standard error. So to make this calculation, we take the 0.135 plus or minus 1.96 times 0.0242. The plus or minus part tells me that I have two calculations to make. So the left hand, which I have at the bottom for LH, of my interval will be 0.135 minus 1.96 times 0.0242. And the right-hand side of the interval will be 0.135 plus 1.96 times 0.0242. So you can see as a proportion, a decimal, we get 0.0876. That should actually be, there's a typo right here. That should be 0.1824, not 1824. And then as a percentage, we have 8.8% to 18.2%. So a couple more things that we can determine once we're given a confidence interval. For this one, we can talk about the margin of error. And the margin of error is just really easy to find. It's just the right-hand side minus the left-hand side divided by 2. Or it's the big number minus the small number divided by 2. So in this case, it's 18.2% minus 8.8% divided by 2 is plus or minus 4.7%. The previous example was a 95% confidence interval. We can calculate other confidence levels, 90%, 99, 80, but 95% is the industry standard. And when we are constructing confidence intervals of this nature, we typically use what's called a Z critical value, and it is 1.96 for a 95% confidence interval. Again, for the scope of this class, you don't need to dive into the weeds and understand this much more, but if you're one of these people that just can't move on without understanding every little particle of this, then there's all kinds of stuff out there. It's pretty well described in your textbook, actually. But three of the common values are the 90%, 95%, and 99%. So we have something called an alpha level, which we'll get into later in hypothesis testing, and then we have the critical values. But for the most part, for this particular type of test, I want you to know that the critical value for a 95% confidence interval is 1.96. Interpreting a confidence interval, there are correct and incorrect interpretations. So a correct interpretation is we could say we're 95% confident that this interval from 0.088 to 0.182 contains the true population proportion. The true population proportion would be the percentage of all residents in this Appalachian town who are diabetic. It's incorrect to say that there's a 95% chance that the true value of P falls between the two values. Now, it's, I don't. Some students have a hard time wrapping their mind around this, but remember, P is unknown. We don't know where P is. We're trying to estimate it. So we can't say there's a 95% chance of P being somewhere when we don't know what P is. So a little caveat to interpreting a confidence interval. Another incorrect interpretation, 95% of the sample proportions will fall between there and there. That's just incorrect. We have one sample proportion. It falls there. It falls right in the middle. It's our point estimate, but we can't make statements like that. Finding confidence intervals of this nature is really easy with StatCrunch. If you just open up StatCrunch to a blank worksheet, go to Stat, come down to Proportion Stat, go over to one sample and width summary. Enter 27 as the number of successes, 200 is the number of observations. Click the confidence level confidence interval and put in 0.95, and then select the method as standard walled. And you'll see that you get the output. Now let's go left to right, and let's talk about what these each of these values tell us. The proportion P is what we're trying to estimate. The count is 27 out of the total of 200. The sample proportion, what we get from our sample data, is 13.5%. The standard error is 0.0241. 6. That's found, wow, you can look it up if you want. I don't want to go down into those weeds. The left limit, the upper limit is 0.08, well, 0.088 and 0.182. We typically report those as a percentage, so it would be 8.8% to 18.3%. All right, gang, that's all I got. Take care.